Our finest speaker before lunch is Jun Cowan from Prestologic. Jun will be speaking on Perkins Discontinuities, structural controlled grade patterns, diagnostic of late orogenic gold and other epigenetic mineralisation. So Jun is well known to many in this audience. He is a Fremantle-based structural geologist consultant specialising in interpreting mineral deposits at the deposit scale. He is the conceptual founder of Leapfrog Software, 2001, and introduced implicit modelling into the mining industry. He has examined more than 600 drilling data sets from around the world. Jun continues to research and develop new analytical techniques that help his clients get the most out of their drilling data, and he enjoys writing thought-provoking articles on geological issues, which can be found on his LinkedIn page. Please welcome Jun.
Okay, it's great, isn't it, to have a room like this and see old friends. And Carl, where is he? Oh, there you are. We're like married couples, aren't we?
Better.
Well, I'm like the wife and you're the husband, right? Because I'm always right.
I think, it's woke and you don't make that distinction anymore.
That's right. Anyway, I'm talking about Perkins Discontinuities. I'll have to explain how this came about. When I joined the mining industry and I started working for Etheridge, Henley and Williams, which was taken over by SIK, they asked structural geologists, do you think our deposit is structurally controlled? And I always thought that's a strange question because, I thought all you have to do is just looking at grade. If you look at the grade, you should be able to figure out whether it's structurally controlled or not. So that's what I've been doing for the last 25 years. So I've been just looking at grade patterns and interpreting them. People talk about shear zone gold, and this is the model that was produced by Simpson. That was published in 1988. Here's a cross-section by Groves and others, 2019, and that geometry hasn't changed that much. Groves did mention that a few gold deposits have clear evidence for presence of crustal scale faults. So I think that's correct. I think that's if you actually start to look at grade distributions in the Yilgarn, for example, it looks rather strange. But not too many people know that how the shear zone model came about. Did you know that the shear zone itself from the model is actually an assumption? It's not based on observation. It was a requirement of their model. But the shear zone model itself is falsifiable, so you can actually test it. Now, the predicted grade continuity of this shear zone model is parallel to the axis into the page. So that's the intermediate axis of strain. So if you measure bedding, shear zones, foliation, and so forth, and if you plot the poles onto a stereonet, this should lie along a grade circle. But this is the sigma gold deposit, and that's a longitudinal section. And you really can't see a horizontal continuity. And in fact, the most distinguishing feature about this is basal zone, and that is parallel to a fold axis. So there's a large fold that is plunging to the east. Not exactly what you predict. And when you start to look at grade patterns in orogenic belts, this is what you see. You can see that there's a tectonic grain here, very prominent. You can actually see that. But the gold deposits themselves are very spotty. And you can see these truncations. So this kind of mystified me as I was, when I was first started to look at this type of data. Why isn't in a shear zone, why aren't the grades continuous along the tectonic grain, parallel to the fold hinges? So if you look along the long axis here, you'll see deposits that have long axes that are vertical rather than horizontal. That's very strange. After I looked at a few hundred deposits, I realized that a lot of them actually lie along fold hinges. That's not mysterious. I thought that was the answer for 20 years, and until recently I came across another paper by Perkins, so this is why I'm talking about this. So why do fold hinge grade continuities just terminate down plunge abruptly? Is there a boundary like this? This is a longitudinal view. This is another deposit. So the symmetry prediction based on the shear zone model just doesn't seem to match reality. So you can see the axial surface and the bedding trace in this deposit. But what are these features here? And these features do not seem to displace the trace of the bedding. So these are what I call Perkins discontinuities. So what are Perkins discontinuities? From Mount Isa, Bill Perkins described this sort of situation where you have a calcite vein. On one side of the vein, you have sphalerite-rich rock. On the other side, you have sphalerite poor. And there's very little displacement across this vein. See that? That's a marker unit there. So he felt that this was diagnostic of post-fracture epigenetic mineralisation. So he was able to show that the sphalerite came in quite late. It wasn't a syngenetic deposit. And that's been supported by other research. So Perkins discontinuity is named after Perkins. I thought he should be recognised for this. Everyone's been ignoring him for about 30 years. So these are discontinuities such as fractures, low displacement faults, veins or dikes and intrusions that are bound asymmetric mineralisation where the asymmetry cannot be explained by fault displacement. Now, this has been seen before, and it's been called damming effect if you go back to the 50s and 40s, okay? So it's not anything new, but it's something that was pointed out by Perkins in relation to Mount Isa. This is another example here. There's a vein. This is a terminating fracture, so this is a rotational. So there's very little displacement across that fracture, and you can see that the asymmetric mineralisation of sphalerite. This is another example, like a silica-rich cherty block, and you can see the black mineralisation there. It can go right across, bleeds along the bedding, lamination, but sometimes it steps across these discontinuities, and sometimes it can stop. So these planar fractures, so the asymmetry cannot be explained by fault displacement. So we address how to work out the timing of mineralisation using Perkins discontinuities, just like how Bill Perkins did at Mount Isa, at the deposit scale though. So it's not hand sample, we're looking at the whole deposit. How do we do this? Well, some people might say, you might have a fracture here or a fault, and you might have asymmetric mineralisation, and this is syngenetic, and that's fair enough. But when you involve a folding here, that's a mineralised unit in yellow, there's a fracture. Now the maximum age of that mineralisation is pre-folding. But it could have happened, pre-folding, after the folding, or after the fracture. But when you have asymmetric mineralisation like this, where the boundary is actually the axial plane of that fold, and you only have mineralisation on one side, then you know that this has to be at least synfolding, the maximum age of the mineralisation. When you have a fracture going right across the fold axis, the mineralisation has to be after the fracture. It'll be after the folding and after the fracture. This is the same sort of situation. So I came up with a little diagram that sort of illustrates these timing relationships. So I'm going to be talking about these styles in circle. I'm going to be talking about 9 different deposits, and these are the gold deposits I'm going to talk about. These are not controversial, so I'll just go through these one by one. The Grasberg situation, where you have the host rocks are folded limestones. You can see the fold axis running like this in northwest, and you have these transverse faults that are running northeast. And you can see that the intrusion itself is actually hemmed in by these faults. The Ertsberg is actually bounded by these faults and also running along the bedding plane. So that's clearly this sort of situation here. You know that the intrusion, the mineralisation has to be after those transverse fractures. Ballarat East. We know what Ballarat deposits look like. They look like that. You've seen these in textbooks. They're repeated over and over again, particularly the saddle reef styles. But do you know what they look like from above? Not too many people know this. They look like that. There are upright folds in the turbidites. That defines the tectonic grain. That's north here. But you have these discontinuities. So I'm zooming up into that area. You can see there's what's called cross-course faults, okay? But the displacement on these faults are not very large at all. You can trace fold axes right through them. But you can note that the grade distribution is quite asymmetric. So you go from this area to here, it's shockingly bad here. And this was noted 100 years ago when the miners were mining. They knew already that these cross-course faults are really important. They called them cross-courses, actually. So this is the same sort of situation here. So this has to be the maximum age of the mineralisation is post-fold and also post-fracture. Or the fractures themselves, the cross-courses are not mineralised generally. This is a deposit of the Carlin trend. There's no controversy about this one. The mineralisation is quite late. You can see this in the down plunge view, a fold shape. Okay? Yeah, looking down plunge, and we're going to go longitudinal section. So those are the boundaries. Those folds go right across those fractures and faults, but they're not all mineralised. They're mineralised in patches, just like the Ballarat East deposits. So again, this is post-fold mineralisation after those fractures. Bronzewing. I'm going to work through some of these deposits in the Yilgarn from north to south. Bronzewing is way up there near Wailuna. So Bronzewing is also a fold-hosted deposit here, and you can see the ultramafics being folded like that. And you have those boundaries that are axial plane to the fold, and you'll notice that the granodiorite is actually dammed up against the pink axial plane fracture. So the mineralisation only happens in that zone. So I'm going to show you the grade distribution here. And I'm going to show you rotating that grade distribution. So I rotate it, and now I'm looking in plan view. You'll see that there are northeasterly trends that cross-cut the deposit and control it. So this is a two-symmetry system. We have the fold axis plunging towards the south, and also there's a steep axis that is defined by those fractures. This is a rotated version of this. So these deposits are segmented because of the northeast striking faults. These are the D4 faults. This was recognised by Julian in 1998, and this is the diagram that he drew. This pattern here, he thought it was important in this area. It wasn't really sort of noticed that much, but I think this pattern is actually quite consistent further south as well. So that's Bronzewing, it's post-fold. We go down to the Bardock zone, we have Sigma deposit right there. Sigma looks like this from above. From sideways, it looks like this. The linear grade plunge within this rich zone is indicated by this. And the way I determine this is by just looking at the data, but also I have an analytical method. I can take the grade data and I can convert that into structural data. Well, data that resembles structural data. I can break it up into grade foliation and grade lineation. So when you actually compute this, the plunge of the system in that package is about 41 degrees to the north-northwest. So when you look in that direction, that's what it looks like. And you can make out a vague fold. And that's the axial surface, trace of the axial surface. And if you rotate that around, you can see how it's been truncated. Okay, so plotting those truncation boundaries, the plunge is towards the west. But you saw before that the plunge of the internal grade is actually plunging towards the north. So there is a two-symmetry system here. This is looking down plunge of the fractures. The fold is plunging towards the north at 40 degrees, and this is looking down the fold axis. And the other deposits around here are all the same. Zoroastrian, for example, is a termination of that deposit in the northern end. There's a whole bunch of deposits. You can notice that most of these deposits are basically tracking the structural grain that pre-existed. And deposits Leilani, and this one down here, Fembark, they're the ones that are parallel to the F4 fractures, but all the other ones are parallel to the tectonic trend defined by the folds. Now let's look at Jundi. Now that I've shown you some patterns, you should be able to actually see these patterns in another deposit. Can you see? No. Brett says no. He refuses to see anything that I show him. Okay, that's what I interpret. I haven't worked on Jundi, but that's my initial interpretation anyway. So that kind of implies that the mineralisation has to be after those fractures. Again, that's the pattern that you see at sigma. So sigma, it's post-fracture mineralisation. Internal fabric is defined by the folds. Okay, so this is an important finding. The axial symmetry of the green arrow cannot be easily determined by examining the internal structure of the mineralised zone, as this would only reveal the red symmetry, okay? So if you're just crawling around in that area here, you'll find out that everything is parallel to the fold. You won't see the boundary. Now, working out the multiple symmetries in your data set is really important for modelling. And this is an example where you have identical drilling patterns, but depending on your assumption of symmetry, you'll get completely different results. And I see a lot of this result up here, with people pressing the button leapfrog. Now, if you don't want to read that paper, you can read my more technical paper, Why Gold Deposits Are Like Tom Cruise and Nothing Like Justin Bieber. For some reason, economic geology couldn't accept this journal. Now, Coolgardie. This is the one in my abstract. You can see the gold continuity jumps across these default faults, and sometimes they terminate against these faults. So again, the mineralisation is late after those fractures. I had Bruce Hobbs do some modelling on how to produce these shapes. He's given actually full talk on this on Ore Deposits Hub about 4 years ago, so you can listen to his lecture. We wanted to know how Perkins discontinuities form. Also, we're interested in why mineral deposits are located in antiform hinge zones. So if you look at Ballarat, those mines are located in antiformal hinge zones. They're not in synclines. You know, if it was a syn-fold sort of situation, you'd expect them in both because you have equal amount of structural permeability developed in the fold hinges, but you don't see that. So when you have a two permeability system here with the flow going upwards, and you have a low permeability inclusion, the fluid flow will divert around that object. If you have a high permeability zone, they get sucked in to this sponge. So it's a bit like a sink. If you have a dipping strata, this low permeability unit will divert the fluids this way, but a high permeability unit would go along almost along that boundary. So if you have an alternating system of low and high layers that are folded like this, they converge towards the antiforms. They diverge away from the synforms. Now, I'm going to take a long section through there, and I'll show you what that looks like. You have a little bit of a fault displacement here. They're producing a hole in a low permeability bed in purple, and the fluids expel out of that zone. So analogy is something like this, you know, with sheep herded through a hole in a fence, and you can predict the amount of the mineralisation happening here. So the massive pile of sheep poo there represents the mineralisation. Note that this is not a trap in the model. In fact, it's actually the opposite of a trap. It's concentrated flow through a hole. And the way I'd like to see it is that these are like inverted bathtubs, and you take the plug out. So Perkins discontinuities, all you have to do is have a highly permeable unit on one side, but less on the other side. And all the fluids get channeled through one side of that fracture. So you can listen to more about that from Bruce. Okay, I want to cover a couple of syngenetic deposits which are controversial. The first one is the Witz deposit and Haile. The Witz deposit is This particular example comes from the West. This is a really neat model that I was able to construct from 2 different papers written by paleoplacer experts. And this is exaggerated 150 times, but you can actually see that this antiform right here contains the thickest reef units. And it's bound up against the fault that is axial to that anticline. And you'll note that the paleoflow is actually right angles to it. That's the grade first, and that's the reef thickness. So this is the grade values. You can see that these fractures here, like particularly here, they define the grade differences. If you look at the reef thicknesses, it's quite clear that the thickest reefs are on this side, and you wouldn't expect that if that was an alluvial system. The paleocurrents are actually, interestingly, parallel to these fractures. And there's no source of where those paleocurrents came from. I can't make it out. I think they must have measured from trough crossbeds or something like that, but I can't find the source. So I have a feeling this might be a bit of circular reasoning around here because they seem to correlate with these fractures. So I think the Wits deposit is post-fold and post-fracture. It's not a paleoplacer. The Haile deposit from South Carolina, this is another interesting deposit because in 2014 the paper was published on the timing of mineralisation. They go into a lot of detail, but I looked at one of their first diagrams. They concluded the gold likely driven by magmatism, not the product of collision, orogeny and metamorphism. When I see the word likely, that means a coin toss. That's the way I interpret it. If you look at their map, can you see what I can see from that map? I'll give you a zoomed up version. The tectonic gland is, as you can see, it's the northeast trending. But you'll see these boundaries that are arrowed that are trending right angles to that. And those boundaries are actually parallel to those younger dikes in black. And when you look at the grade, you can clearly see where all of those dikes are. That's showing the high grade. You can see that the grades stop at the dikes, which means that these fractures existed before, and the mineralisation stopped at those fractures, and the dikes came in through those fractures later on. So the Haile is also post-fold. Okay, like I said, these discontinuities with asymmetric mineralisation, which I call Perkins discontinuities, are not new. The oldest paper that I could find was from 1857 from Cuba. It's interesting that I looked at a whole bunch of deposits and I don't really pay much attention to their compositions, but I've seen these structures in lots of VMS deposits, so yeah, something to think about. In concluding, our interpretations are falsifiable. You can go out in the field and test these. This is based on approximately 1,000 drilled deposit all around the world. Perkins discontinuities feature in many epigenetic deposits, like such as gold, but also there are in other syngenetic deposits. We predict that many more deposits will be identified to be epigenetic in timing from the identification of Perkins discontinuities, and most of these will be discovered by exploration and mining companies, I believe. Now, to understand how gold deposits are formed, I think it's essential to study the emplacement mechanism of non-gold deposits as well. Thank you very much.
Thanks very much, Jun, for a very interesting and illuminating talk. I'm sure there will be questions.
Yeah, I don't need it, probably. Yeah, Jun. It's very interesting because I've noticed in repetitive structural geometries of orogenic gold that these cross structures exist, and I think that means that the gold was there after they formed. And a lot of yours are 70 degrees to the prevailing trend. Do you understand? All of mine are about 70 or 110 degrees. Do you see as a reason for that at all?
No, they come in a variety of angles, actually, yeah. So in my talk, I've only showed things that you can actually interpret in plan. There are systems where the intersection of those those faults are horizontal. So they come in variety of orientations, yeah.
Okay. So thank you, June, for a very interesting and illuminating talk.